Hello everyone, I am Yoko Shibuya. Today I'm going to present a paper titled Selfish Mining Attacks Exacerbated by Elastic Hash Supply. The paper is co-authored with Go Yamamoto, Fuhito Kojima, Elaine, Shinichiro Matsuo, and Aron. Let's get started. As many of you may know, selfish mining strategy, originally proposed in a paper by Aron 2013, shows that the deviant mining can be more profitable than following Bitcoin protocol. Since selfish mining can be a threat to the security of the cryptocurrency systems, many papers have followed and analyzed the effectiveness of selfish mining. However, there is an important limitation in prior work. The literature does not consider how honest miners react to changes in profitability when selfish mining attacks occur. In other words, they simply assume that the mass of honest miners in the system remains unchanged before and after the attack. In this paper, we highlight and solve the issue. First, we empirically show that the honest miners do react to the profitability of the system. In the data, the total hash power increases when the profitability of the system increases, and we call it elastic hash supply. Second, we extend the model of Aron 2013 with an assumption of elastic hash supply. Our main finding from the model is that the effect of selfish mining attack is exacerbated under elastic hash supply assumption. We go over empirical and theoretical studies, but before jumping into the empirical study, let me briefly explain what selfish mining strategy is and how elastic hash supply assumption is going to change the effect of selfish mining. So, what is selfish mining? The idea is very simple. A selfish miner keeps its discovered blocks private and thereby intentionally forking the chain. Consider a situation where a public or main blockchain has discovered 3 blocks. And let's suppose that after the second discovery of the public blockchain, a selfish miner discovered 2 blocks while the public blockchain finding the 3rd one. In this case, the selfish miner chooses to keep the discovered blocks a secret. All other nodes on the network continue to mine on the public chain, while the selfish miner continues to mine on its private branch. If the selfish miner discovers more blocks, then it develops a longer lead over the public chain. Eventually, the public chain catches up to the private chain, and the private chain can immediately time its release of the private blocks to the public and having the longest proof of work. By following this strategy, the selfish miner can increase the share of mining rewards out of the total mining power in the system, because the other miners waste their mining power on mining unnecessary blocks, and an attack reduces the effective mining power in the system. This is the logic behind the selfish mining generating more revenues than honest mining. But this logic assumes that the total hash power in the system is fixed. In practice, however, most miners are profit-oriented and choose which currency to mine based on the profitability. Therefore, the analysis that assumes the total hash power being fixed misses an important interaction between the reduction in profitability due to the selfish mining and total hash power in the system. So, what happens if honest miners do respond to the change in profitability? A high-level summary of the effect of selfish mining and the elastic hash supply is summarized in the flowchart. When the selfish mining attack happens, the profitability of honest miners goes down because their mining power is wasted on finding blocks that are not going to be the longest proof of work. In response to the reduction in profitability, honest miners leave the system. Then, two things happen simultaneously. First, as honest miners leave, the impact of the attack on the remaining miners is magnified because a higher fraction of their mining power is now erased, which in turn drives more miners away. At the same time, as honest miners leave, the total mining power decreases. Therefore, the mining difficulty drops and mining becomes cheaper. This second effect somewhat counteracts the decreased profitability for honest miners. If the first effect dominates, then the effect of attack is magnified so that all honest miners might leave the system. If the second effect dominates, then positive number of honest miners stay in the system. In the theory part of the paper, we analyze which effect will dominate the equilibrium and what parameters are important to determine the relative size of the two opposing effects. Here, we could already expect a sizable effect of introducing elastic hash supply assumption into a model. But you might doubt how realistic the assumption is. So we decided to look at the data and check if indeed the total hash power responds to the profitability in the system. Here is our empirical analysis. Our goal in the empirical analysis is to measure the correlation between total hash rate and miners' revenue in the data. If we find that they are positively correlated, it means that miners respond to the profitability in the system, and we can conclude that the elastic hash supply assumption is realistic. We try to measure the correlation between total hash supply and miners' revenue using data from 3 different cryptocurrencies: Bitcoin, Ethereum, and Ethereum Classic. However, we faced one difficulty. Measuring correlation between 2 time series data often suffers from the existence of long-term trends in the data. For example, both total hash rate and miners' revenue have increasing trends over the past 5 or more years due to the technological advancement in cryptocurrencies. If we measure the correlation between them, we will find a positive correlation because they're correlated in long term. But what we want to observe is that short-term correlation. Whether the miners react to the change in profitability a few seconds ago or a few hours ago, not the change in profitability from 5 years ago. The strategy we took to deal with this problem is to apply time detrending methods commonly used in economics. Please see the figure. The blue line in the figure shows the total hash rate in Bitcoin from 2017 to 2020. You can see that although there is a short-term fluctuations, there is a huge increasing trend over the years. What time detrending methods do is to extract the long-term trend from the time series data. In the figure, time detrending method detects the red line as a long-term trend, and if you eliminate long-term trend, it gives us short-term movement, which is called cycle components, shown as a green line in the figure. By measuring the correlation between cycle components of total hash rate and miners' revenue, we can properly measure the short-term correlation between them. In the paper, for robustness purpose, we used 3 different time detrending methods: Hardwick Prescott, Baxter King, and Cristiano Fitzgerald filters. Each filter has a slightly different method of separating a trend from cycle. The table reports the correlation between total hash power and miners' revenue in 3 different currencies and with 3 different time detrending methods. We used daily data of total hash power and miners' revenue from 2017 to 2020. The row that is highlighted in red shows the coefficients of linearly regressing the change in log of hash rate on the change in log of miners revenue. The coefficients vary across different currencies and different time determining methods, but with any type of time determining methods and any type of currencies, the correlation between the total hash rate and miners revenue is positive and statistically significant. The result shows that hash supply is positively correlated with miners revenue, which is the evidence of elastic hash supply. Motivated by the evidence, we introduced elastic hash supply assumption to a model of selfish mining. We introduced elastic hash supply by imposing so-called free entry condition into the model. Free entry condition assures that miners enter or leave the system until the profitability of mining in the system converges to zero. For example, when there is positive profitability in the system, more miners enter, seeking the profit, and they keep entering until the profitability becomes zero. Under the free entry condition, equilibrium hash power of honest miners, which is defined as H star, is determined when the profit is equal to zero at H star. Starting from zero profitability, selfish mining attack reduces the profitability to negative and forces some honest miners to leave the system. Then, two opposing effects come into play. First, attacking pool's relative mining power increases, and thus profitability of honest miners further decreases. Second, since total hash rate decreases by the exit of honest miners, profitability of remaining honest miners increases. The question is, which effect will dominate in equilibrium? It turns out that there exists a threshold mining power for attacking pool, where if initial mining power of the attacking pool is below the threshold, positive number of honest miners stay in the system. If initial mining power of attacking pool is above the threshold, all the honest miners leave and the system collapses. It means that if the attacking pool's share is large enough, the negative propagation effect dominates, and the selfish mining attack forces all honest miners to leave the system. The threshold mining power for attacking pool depends on a parameter gamma, which is defined as the ratio of honest miners that choose to mine on the attacking pool's block. When gamma equals 1, which is the most preferable case for attacking pool, the threshold share is about 29%. Even when gamma equals 0, which is when none of the honest miners would mine on the attacking pool's block, the threshold share is about 34%. It means that if the attacking pool's initial mining power occupies more than 1/3 of the total hash rate, the selfish mining attack can be so effective that all the honest miners leave the system. This negative propagation effect is not present when we assume fixed hash supply. Therefore, we can conclude that the effect of selfish mining is exacerbated under elastic hash supply. Lastly, let me talk about possibility of multiple equilibria in the model. We find that when the attacking pool's mining power is below the threshold, there are two possible equilibria where positive number of honest miners stay in the system. The figure shows honest miners' revenue and cost as a function of honest miners' mining power. Under the free entry condition, the equilibrium is determined when revenue and costs intersect, where there is no profits made. There are two intersections in the figure, H1 star and H2 star. H1 star is an unstable equilibrium. A slight increase in miners' revenue would make positive profit for miners and make more miners enter the system. Eventually, the system converges to H2 star. If there's a slight decrease in miners' revenue from H1 star, then the system produces negative profit and forces all miners to leave. Eventually, it converges to where all miners leave the system. In contrast, H2 star is a stable equilibrium. A slight change in mining power from H2 stars forces the system converges back to H2 star. Let me conclude. An important limitation in the prior models of selfish mining is that they do not take into account honest miners' reaction to the change in profitability. In this paper, we first showed that in practice, total hash rate responds to miners' revenue in short term. That's what we call elastic hash supply. We then introduced elastic hash supply into the model of selfish mining by imposing free entry condition. We found that the effect of selfish mining is exacerbated under elastic hash supply. The selfish mining attack has a potential to collapse the whole system if the attacking pool's mining power is large enough. Future work includes analyzing the effect of hash supply in different attacking strategies. It will also be interesting to extend our static model to a dynamic context. Thank you very much for your interest and attention.